Alright, let's show that in a ring things happen. So, we're going to start with the first statement. We take these guys in R. No. Wow, I wrote bold R, but it should just be normal R. Then, what is a B minus C? This is just a B plus negative C. Then you distribute it, minus C. But we know we discuss in this section that you can bring out that negative sign. So then, by generalized, why is the bottom thing there? Shouldn't be there. Why distributivity? If n is the natural numbers, that does not include 0. Natural numbers is 1 through just 1, 2, 3. All integers that are not negative and not 0. 0 took years to come up with. It didn't come around until I don't know, 580, 1080, somewhere in there. Maybe 800-ish. But there are numbers before then, so it kind of seems like it would be unnatural if it wasn't always considered a number. So I don't know why people call it natural, but no. The point really is that natural numbers are useful for labeling things. And so that's what analysts like to do. Like you have a countable collection of things, and you need to label these things, and you number them 1, 2, 3, 4, and so on. Whereas if you're doing algebra, then typically you're referring to a group, and if you're in a group, you need to have an identity. And so sometimes, well, not a group, but a monoid. So if you're looking at the monoid of positive integers or non-negative integers, then you're going to want to have 0 in there. So anyways, I think it seems to me that algebraists tend to include 0 in the natural numbers and analysts tend to not include 0 in the natural numbers. I don't know if that's generally true. It's just what I've seen. I like to not include 0 in the natural numbers, so that's what I'm going to do. And if you don't like that, then leave a really, really angry comment and I'll ignore it. So, NAB, well, this by definition is just AB added to itself n times, but when I say generalized distributivity, I mean that you use induction on distributivity to you can factor something out of not just the sum of two things, but a sum of n things. So basically we can a plus all the way through a b. So you basically pull that b out because you can factor it out of all these terms. But what is this? In there we've got n of these sums because we had n to begin with. So this is NAB. And NAB is also equal to, we do the same thing, but we do it this way, A and B. Okay, so that's when n is in the natural numbers. We want to prove, okay, so NAB equals A and B. So we want to prove this thing for all integers. We've proved it for natural numbers. So next, when n equals 0, NAB equals 0 equals A and B, so it's obviously true. Finally, if n is in Z and n is less than or equal to -1, then write n as -m, where m is in Z. No, natural numbers. Because that's the point, because we're going to apply the thing that we know already. So then, NAB equals minus MAB, but we know from before that this thing on the inside here, we can make this minus MAB, but we can bring that minus sign inside, and that's just NAB. And also, I'm going to try to fit this. We do a similar thing, minus A, MB, A minus MB, A, NB. So, NAB equals ANB. Yes, I got it. Okay, so that holds. So it holds for all integers n, because we proved it for natural numbers, negative natural numbers, and 0, and that covers everything. So there we go. We're done.